and you draw a tangent line, okay, it touches the circle at one point, okay, it's like right angles to the radius. That's what we'll talk about tomorrow is tangent lines. So you've got tangent lines when your velocity is changing. So since this is continuously becoming more steep, that means this thing is speeding up. Now, I'm speeding up now. What's happening here when that line begins to flatten out?
Slowing down.
I'm slowing down because I'm approaching being at rest. Okay? The griddle. Did I start at the reference point? No. Do I have to start at the reference point? No. Where did I start? Like let's say here's Al. We'll have him be the reference point. Okay? Like we did yesterday. So let's say this side over here was that side. You guys set that side positive. So where am I at when I start?
Like almost like the 1 kilogram masses.
Yeah, so maybe something over here, right? So if I said, okay, here's this position time graph and act it out. I would start here, and then what would I do?
Move to the right.
Move, I'd speed up, and then I'd slow down, pause for dramatic flare. Then what?
Run over to the other side.
Well, I'd come back, right? Okay? Now, I'd go past the reference point, true?
Yeah.
But when I go past the reference point, does my velocity change sign?
No.
No, why?
Because you can change direction.
Beautiful, nice. Okay? Now, when you have a straight sloping line on a velocity time graph, this is what we call constant velocity. Now, this is a simple truth, but it makes life simple. Every motion that you're going to have, that you're going to look at, can only be one of two things. Okay? There are only one of two options. Either your velocity is changing, meaning that you're speeding up, slowing down, or changing the direction. Or you have constant velocity and your velocity vectors aren't changing. Okay? That's it. Every second that you have been on this earth, those have been the two possible things that could have happened. Ever since you could crawl, okay? Either you were at rest, like in blob stage going, ah, okay? Yeah, blob stage. Y'all have been there, okay? Or even when you started to crawl, wow, here I have velocity vectors, right? And now you're playing soccer and you're good. And now not only do you guys have velocity vectors, then you're kicking the ball and you're giving velocity vectors to the ball, right? Okay? And so you've been just dealing with velocity vectors your entire life. You haven't thought about it, but you have, okay? Even when you drive. What's the purpose of the gas pedal in terms of velocity vectors? Make the velocity vectors bigger. What's the purpose of the brake? Make the velocity vectors. What's the purpose of the steering wheel? Change the direction of the velocity vectors. Okay, that's it. Right? When you play soccer, right? You are continuously. It's a game of vectors. That's what you're playing. You are playing a game of vectors. Whether it's the ball, whether it's you guys trying to defend it. If it's football, it's a game of vectors. Okay, that's it. All sports are a game of vectors if you think about it far enough. That's what it is. Okay, now, so when you look at the slope on a position time graph, it can only do one of two things. It's either going to be a straight sloping line or a horizontal line indicating that the slope is constant or the slope is changing, which means you're speeding up and slowing down. That's it. There is nothing in between. Every problem I will give you can only be one of two things. Either you're at constant velocity or you're speeding up or slowing down. That's it. That is the only, those are the two tricks that I've got up my sleeve. That's it, nothing else. So, you're here, I'm speeding up, I stop, I come back. Now, what's happening here? Mr. Stanley, what am I doing here?
You're slowing down.
How do you know?
Because the slope is left.
Beautiful. Okay? How many times did I change direction? Tori, how many times did I change direction?
Once.
How do you know? It's a good answer. How do you know? What's the first golden rule? If an object changes direction,
The velocity changes sign.
beautiful. Okay, said with no confidence whatsoever, but that's a good answer. Okay, so if an object changes direction, the velocity changes sign. So here I've got positive slope, and then I've got negative slope. Now, if you're a math nerd, okay, anytime you see like a relative maximum or a relative minimum, that's when you're going to get a direction change. Okay. Now, if this had been a line like this, where it was more like a peak, Then you can get into like tangent lines, and that velocity goes to 0 when you change direction. So like I take Gary the golf ball, and I throw Gary the golf ball up in the air. Does Gary the golf ball change directions?
Yes.
Yeah? So when do you think the velocity goes to 0?
When it's
At that highest point, okay? That's when the velocity goes to 0, because you're going from a positive velocity to a negative velocity. So that's what's going to happen on a position time graph. Got that? Okay. Now, let's talk about velocity time graphs. Okay? Okay, so here's the deal. Madeline has the nerd package on her car. So instead of displaying this in miles per hour, her speedometer measures in meters per second. Okay? Okay. Now, Bree is the co-pilot, and she has the stopwatch, right? So here's what's going to happen. We're going to keep track of how fast Madeline is driving as a function of time. Okay? So you've got a stopwatch, you're looking at your speedometer. Okay? So you're in the parking lot. I like the visual. Okay? So you're in the parking lot, you're at rest, right? You've got a stopwatch. So you press down on the gas pedal. What's the purpose of pressing down on the gas pedal?
To go forward.
You go forward to create a velocity vector, right? Okay, because you don't have one and you want one, because you're not going to move without a velocity vector, right? So the purpose of your gas pedal is to make that velocity vector bigger. So here's the carrot car, right? We're here, right? V naught equals 0. So what does the naught mean?
Initial.
Initial. So we're at rest. So over a period of time, I'm going to do this a lot. So she's pressing down on the gas pedal to make her velocity vectors bigger. So Bree at the end of 2 seconds goes, okay, hey, 2 seconds, how fast are you going? So Madeline looks at her speedometer and realizes that she's going 6 meters per second, okay, which is a decent clip. I mean, you can run faster than this. So she, you know, like if she's going down the street, this isn't like warp speed, okay? But it's not bad, 6 meters per second. So we got a line that's going to come up like this. Okay, imagine that's a straight sloping line. Okay? So here's the question. So we're at 2 seconds, 6 meters per second. Did we accelerate? Yeah. How do you know? What'd you say, Mary?
Velocity change.
The velocity changed. I went from 0 to 2 meters to 6 meters per second. Oh, I accelerated. Okay? Now, here's the story. Do you think you can find the slope of that line? Felix, could you find the slope of that line?
Yeah.
What would the slope of that line be? You're in a physics class, not in a math class.
What?
You're in a physics class, not in a math class. So keep that in mind when I ask you to find the slope of the line.
Confused now.
Okay, pretend you're in your math class.
Yeah.
You're going from 2 to 6, right, and you started at 0, 0. If you're in a math class and I said, what's the slope
Oh,
of
it's
the line,
just 3.
what would you say?
3.
3. That's the mathematical answer, right? I want the physics slope. So what else do you need?
Unit.
So what are the units?
Meters per second. Or,
Let me give you a hint. Can I give you a hint?
yeah.
Okay? So you got 6 meters per second minus 0 divided by 2 seconds.
Meters per second. Meters per second squared.
Beautiful, right? So 3 meters per second squared. Now, what's measured in meters per second squared? Oh, acceleration. That's kind of cool, right? So what does the slope of a velocity time graph give you?
Acceleration.
Acceleration. Ah, which golden rule are we up to? Number 3?
Yes.
Okay? So golden rule number 3. The slope of a velocity time graph gives acceleration. Okay? So the slope of a position time graph gives velocity. The slope of a velocity time graph gives acceleration. Okay? Cool with this? Good. All right. Yeah, don't memorize it. You just look at the units, whatever works for you. Okay? Now, let's go back. Oh, wrong way. So here's the car, right? So here's Madeline's cute little carrot car, right? She's at rest. We get to V1, V2, right? And eventually we get up to 6 meters per second. Now, pretend that you're in a math class. Felix, pretend that you're back in a math class. Don't worry about the numbers. Don't worry about anything else. You're in the math zone. Is the sign of this slope a positive or negative number? Positive. Oh, right now, pretend that you're back in the physics room, which you are. So the slope represents acceleration, right? So if I have a positive slope, I also have positive acceleration. True? Okay. So here's what I want you to look at. I got positive velocity, I have positive acceleration. Felix, am I speeding up?
Yeah.
Yes. Even freshmen can't go any slower than 0. I've seen some try. Okay? If you're at 0 and this line moves, what do you have to do? Speed up, right? You cannot go slower than 0. That's it. You cannot do it. Okay? Physically impossible. So, but here's what's important. One of two things can happen, and only one of two things can happen when you look at acceleration problems. And there's only 2 tricks. When you have any acceleration problem, only 2 things can happen. You're either going to speed up or you're going to slow down. Now, eventually, we'll make you move in a circle where we change the direction of the velocity vector. That's a ways down the road. So literally, every acceleration problem I give you, I can only make it do one of 2 things. I can either make it speed up or I can make it slow down. That's it. There is no other thing that I can do. So no matter how complex the problem is, ask yourself, am I speeding up or am I slowing down? That's it. Okay? There's nothing else I can do. Okay? I can't, oh, I'm kind of accelerating. No, you can't kind of accelerate. Okay? Either you are or you aren't. Now, here's the deal. Notice that I have positive acceleration and I have positive velocity and I'm speeding up. So here's the next golden rule. Whenever acceleration and velocity have the same sign, you speed up. Whenever they have opposite signs, you slow down. So let me write that up. Okay? So here's golden rule number 4. So if velocity and acceleration have the same sign, you speed up. So if they have opposite signs, what do you think you're going to do? You're going to slow down. So if they have opposite signs, you slow down. So, and there is no like, oh, that's always true except for, okay? There is no except fors in this situation. None. 0, zip. 0. None. So literally, again, every acceleration problem I give you is either going to make you speed up or it's going to make you slow down. That's it. Okay? That's it. So as soon as you say, hey, here's a plane landing on an aircraft carrier, and it's going to be brought to a rest. It's going to be stopped. Right away, as soon as you see it's going to be stopped, what do you know about velocity and acceleration? Opposite signs, right? A train is, leaves the station and speeds up to 20 meters per second. What has to, you're going from resting, you're speeding up. What about the sign of velocity and acceleration? Same sign. Literally, every problem, that's the first thing that you need to decide. Is this thing speeding up or is this thing slowing down? If they're opposite signs, you're slowing down. If they're the same signs, you're speeding up. So no matter how complex the problem is, start with that idea. So let's say I take Gary the golf ball, and I throw Gary up in the air. Okay? So on the way up, what's Gary doing?
Slowing down.
Slowing down. So what do you know about velocity and acceleration?
They're opposite.
Opposite signs. On the way down, he is.
Speeding up.
So therefore, velocity and acceleration have to have same sign. Boom, there you go. You've solved half of gravity right there. Okay? Literally. You've understood half of all gravity problems right there, if you just keep that in mind. Now, let me show you how this deal plays out. So this is kind of going to be golden rule 5-ish, okay? In terms of how we show constant velocity. And you have to realize how this is shown on different graphs. That's T. Okay? So let's say that you've got a position time graph that looks like this. Okay? That's a straight line. Okay? So Matt, if this is a position time graph with a straight sloping line, how is that going to show up on a velocity time graph? And that's 0 meters per second right there.
Okay.
Matt, what does the slope of a position time graph give you?
Velocity.
Is this a constant slope?
Yes.
So therefore, I'm going to have a...
Constant velocity.
So how do I show a constant velocity, you think, on a velocity time graph?
That was a straight line.
Right? So this is going to go across like this. It's going to be some positive number. So now, with that in mind, if I come back over here to the problem here, okay? So here we were. Madeline hit the gas. She sped up. Now, she's going to maintain the constant velocity with a horizontal line. So anytime you see a horizontal line on a velocity time graph, guess what? That means you're at constant velocity. So think about this. Your gas pedal does what to your velocity vectors?
Changes.
Makes them bigger. Your brake pedal makes them smaller. Your steering wheel changes them. What's the purpose of cruise control?
Keeps it the same.
Yeah, so cruise control is a function of maintaining a constant magnitude of your velocity vector. Okay, that's the purpose of cruise control, is to maintain a constant magnitude. Now, you can still turn the steering wheel, right, and you can change the direction, but the purpose of cruise control is to maintain a uniform velocity vector as you're driving down the road. So, speed up, slow down, change it, the direction, but then you also have a device to keep it constant. Oh, okay, right. Now, so I'm here, I started at rest. I sped up, I'm cruising along, okay? Cruising along. Now at this point, because Madeline is a nice person, she sees like a squirrel run out into the street, okay? And she likes squirrels, right? So she's going to hit the brakes, right? So what's that graph going to do as soon as she hits the brake? Like this, right? So when she does this, okay, here's the big kicker. Hunter, is this a positive or negative slope?
Negative.
Negative. So that means that's also the sign of my,
Velocity.
nope, because my velocity is still positive.
Acceleration.
Sign of my acceleration. So now I have negative acceleration, but my velocity is still positive. So now, I have positive velocity, negative acceleration. They are opposite signs, so what am I going to do?
Slow down.
Now I'm going to slow down, right? So I was speeding up here, constant velocity, and then I'm going to slow down, because now they have opposite signs, right? So she's going to go, whoop, hit the brakes. How do you know that she did not change direction?
The velocity sign stayed the same.
Yeah. Velocity never went below 0. Okay? The velocity never went into the negative region. So here's what happened. So the resemblance is not striking at all, but again, okay? So here's Madeline, right? We'll get the hair for dramatic effect, okay? So she's here, right? She hit the gas pedal, she sped up, then she maintained a constant velocity, and then what?
Stop.
Hit the brakes, right? How do you know that she did not change direction?
And go into negatives.
Well, what did not change sign?
The velocity.
The velocity did not change sign. Now, did the acceleration change sign?
Yes.
Yes, but how? So your accelerations can change sign without changing direction, which happens all the time, right? You're driving along, you hit the gas pedal. Oh, hey, you're speeding up. Oh, you hit the brakes, you slow down. But you didn't change direction, okay? That's not what happened. You could, but you didn't have to. Great question, or just a big stretch?
No, I was wondering, like, since like you can't, since you're always like accelerating,
Yeah.
like in deaccelerating is not a thing, right?
Oh, no.
Sorry for even saying it. Sorry.
Yeah.
But so like, how come you can have a negative acceleration, even though you're not necessarily, you know what I mean? Like you're not negatively.
Just you give me about a minute, and I'll answer that question.
Okay.
Okay? And if I haven't, remind me.
Okay.
Okay? Now, so here's what I want you to get out of your minds right now. That positive acceleration always means that you're speeding up, and negative acceleration always means that you're slowing down. It can, okay? It can. But let's look at this. What do you think it would mean if I continue this line down here like this? What do you think happens here?
There's a change in direction, maybe.
How do you know there's a change in direction?
Just there's a change in sign.
Velocity changes sign, right? So, because it's the same slope, do I still have negative acceleration? Yeah. But that negative acceleration now, look at this. Here's 0. Now, once I cross this line, what's the sign of my velocity?
Negative.
But now I still have negative acceleration, and I'm going to... No, I can't go,
You're gonna
I can't
get
go any slower than
Constant
0.
velocity.
My velocity, I'm going to start to speed up, right?
Yep.
So here's what happened. Okay, here's the car. We were at rest. We sped up, constant velocity, slowed down, hit 0, and then we're going to go back in this direction. And I know I'm going to do that because my velocity went from positive to negative. So I can have the same acceleration and change direction. But I can't change direction with the same velocity. Does that make sense, Great? So here's the deal. In this situation, I've got negative acceleration and negative velocity, and I am speeding up. Now, what's happening with the horizontal line here? What am I doing? Or what's Madeline doing? Constant velocity. Now, let's say she hits the brakes. What's this line going to do when she hits the brakes?
Go up.
Hunter, what does this mean?
Shoot straight back up to 0.
International sign for a positive sloping line?
Yeah.
Okay, or a score in Australian rules football, one of the two, okay? So let's go with this. So, now, what's this? Did my acceleration change sign? Vonda, did my acceleration change sign? So now I have positive acceleration with negative velocity, so what am I doing? Speeding up or slowing down?
Slowing down.
Beautiful, okay? So here I've got positive acceleration with negative velocity, and now I'm slowing down. So this is the classic situation where you get out of your minds that positive acceleration always means that you slow down, or speed up, and negative acceleration means that you slow down. It can happen, but it isn't an absolute golden rule. Because here I have negative acceleration with negative velocity. Guess what? I'm speeding up. Here I have positive acceleration with negative velocity, and I am slowing down. Okay? So the reason that I hate the word decelerate is because it just confuses you. Okay? If you look at Newton's second law, it only exists as force equals mass times acceleration. There isn't, like on the back side, it doesn't say force equals mass times deceleration. Okay? This is why I hate the word decelerate, because it's just confusing. Because the slope of a velocity time graph will only give you acceleration. It will not give you deceleration. So, Alyssa Papan, I don't know if you follow her on Twitter.
Oh yeah, I saw that.
Oh yeah, so she was in a math class in college and sent out a tweet that says, you know, like she can't even focus on the lecture because the guy is using decelerate, and she blames me for it. And it's like, I'm not responsible for what happens with you. But here's the deal. So again, only one of two things can happen here. You're either speeding up or you're slowing down. or you have constant velocity. That's it. Now, so let's go back to what we were talking about here. So, if I've got a straight sloping line on a position time graph, that's shown as a horizontal line on the velocity time graph. Now, we haven't talked about this, but we will briefly. Here's an acceleration time graph, okay? An acceleration time graph. So, if my velocity is constant, what's my acceleration? Don't make this difficult. There just isn't any, right? Okay, there is no acceleration because my velocity is constant. So on an acceleration time graph, that would just be a horizontal line at 0 meters per second squared. So straight sloping line here, horizontal line here, I got nothing here. Okay? Now, how would this change if this was a downward sloping line? What's the only thing that would change on my velocity time graph? Yeah, then it would be down here in the negative region. Would my acceleration still be 0? Yeah? Okay, that's cool. Now, let's talk accelerated motion, which is a little bit more complicated. So let's go to rule number 6. Accelerated motion. So, start with the position time graph. Okay? So, here's my position time graph, right? Nick, am I speeding up or slowing down?
Speeding up,
How do you know?
because it's like it's getting steeper
It's getting steeper. So how can I show this on a velocity time graph?
by also having it get steeper.
So, but like,
Or having
curved
it go up
line, straight line.
straight.
Straight line. Now, this, on a velocity time graph, this is what we call uniform acceleration. Now, the beauty of this is the only type of acceleration you all will have to worry about, okay, is uniform acceleration, which means it's a straight sloping line. This, in reality, is tough to do. Like, your cars never exhibit uniform acceleration, meaning like the velocity changes the same amount each time. But it's a nice model, because otherwise, this gets curvy, and it just gets real ugly, and we're not, okay? So anytime you're talking about acceleration, we're going to call that uniform acceleration. Okay, so here's the question. How would that show up on an acceleration time graph? Would it be at 0, above 0, or below 0?
Above
Shively. Home. 0. I would have no acceleration. Let's think this through. Alrighty. Okay. What does the slope of my velocity time graph give you? So is my acceleration a non-zero value? Yes, because my slope is a non-zero value. Is the slope positive or negative?
Positive.
So on my acceleration time graph, this is just going to be a horizontal line with some positive acceleration. Does that make sense? So, for those of you that do the calculus thing, okay? So, if you take the derivative of your acceleration, you get your velocity. If you take the derivative of your velocity, you get your position, okay? So, that's why it goes a constant to a linear to a quadratic function. Actually, it goes derivative, or integral. Okay, now, here's the next thing. What if I had a position time graph that looked like that? So what does that indicate? First off, am I speeding up or slowing down?
slowing down.
And from here,
Oh, you're speeding up.
speeding up, right? Isn't the velocity getting bigger? Right? Now, is the velocity negative? Yeah. So, how would that look on a velocity time graph?
It'd be negative.
It'd be in the negative region. It would start at kind of zero-ish, and then do what? Go
Or negative.
down like that. Would I have negative acceleration?
Yeah.
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 Would I have negative velocity?
Yeah.
Yeah.
That would mean that I am
Speeding up.
speeding up, right? Now, Shively,
Yeah.
what would my acceleration time graph look like?
Be like below the flat line, you know, straight.
Yeah, that's even worse. Not only did I flatline, now I'm talking below the flat line. Wow, that hurts. Okay? So maybe something like that?
Yeah, that looks good.
Ah, cool, right? So literally, here's the deal. You're either going to speed up, slow down. That's it. Either your acceleration is a non-zero value and you're speeding up or slowing down, or you have no acceleration and your velocity is constant. Those are the only two games in town. That's the only thing I can do on these problems. Okay, that's it. I only have those tricks up my sleeve. And if you keep that in mind and you read the problem and go, wow, hey, this thing's speeding up. Right away, I know velocity and acceleration have to have the same sign. If I'm slowing down, they have to have opposite signs. That's it. Literally, if you keep that in mind, 90% of acceleration and velocity problems will take care of themselves. If you just keep that in mind. Now, math class, okay? And I'm going to give you a rectangle, okay? Give you a rectangle. And I'm going to tell you that this thing is 8 by 5, okay? So how would you find the area of that rectangle, class? Length times width, right? And you would take 8 times 5 and you would get 40. Now, for probably the past 7 or 8 years of your life, what have you been drilled in terms of expressing area? What do you always do with an area? What has it always done?
Squared.
Something squared, right? Meters squared, inches squared, light years squared, something. Okay? So maybe that's meters squared. And up to this day, August 28th at 12:30, you all have been always told that area isn't something squared. Okay? That's it. Full stop. That's all you have to remember. I want you to keep this in mind. Now, I want you to look at something else. So, let's say that Shively is going to run at 8 meters per second for 5 seconds. Shively, how far are you going to run?
40 meters. Wait,
Don't not make this difficult.
40 meters.
40 meters.
Yeah.
Not 42.
No.
Oh, okay. 40 meters, right? Okay? Because the seconds cancel out, you get meters, boom. So all we're saying here is the distance traveled is velocity times time, right? No worries. Y'all can do this. Y'all have done this a long time, okay? Old hat. And so if you take a velocity times time, you get a distance. Oh, that's cool. And then if you go back, you say, oh, area is always is measured in something squared. Okay, cool. Now, here's the million-dollar question. Shively's here, right? And he's running at a constant velocity of 8 meters per second for 5 seconds. Okay? That's what he's going to do. So, Olivia, here's the velocity time graph. How can I show Shively running at a constant velocity of 8 meters per second? Okay, here's 0. Here's 5 seconds. How can I show Shively, that's tough to say, running at a constant velocity of 8 meters per second for 5 seconds? What's that going to look like on a velocity time graph?
Horizontal.
Yeah. At?
At positive.
So here's 8, right?
Yes.
So is it going to start here and go up to here?
No. That's
Why not? Why won't it start at 0 and go up to this point? What kind of velocity do I want Shively to have? Accelerated motion or constant velocity? Constant velocity. So if you draw a sloping line, that indicates that he is,
speeding up.
that's right, he's not speeding up. He's moving at a constant 8 meters per second. So how can I draw that?
I just one.
Horizontal line
Yes.
at 8 meters per second.
Yes.
And stopping it at
5 seconds.
kind of this action.
Yes.
Okay, that's cool, right? Okay, I like that. Now, I'm going to find the area of this rectangle, and this is where you all are going to flip out. I'm just going to tell you right now, okay? So I have a rectangle that has a dimension of 8 meters per second by 5 seconds, okay? That's the dimensions. I got 8 meters per second times 5 seconds, and you're going to get 40 meters. And you're going, whoa, area has to be in something squared, right? This is wrong, Mr. Burkham. What is this evil you're speaking of, okay? And now I have, I have dimensions in velocity and time. Whoa, you can't have dimensions in velocity and time? Sure, I just did. I've got a dimension on the height of a rectangle that's 8 meters per second. I have another dimension that's 5 seconds. Looks like a rectangle to me. Looks like a duck, quacks like a duck. Guess what? It's probably a rectangle in this situation. So, when I find this area, what am I finding?
Distance.
Not distance. Close. It rhymes with displacement.
Displacement.
I'm finding displacement. Okay? Finding displacement. Now here's the reason why. The reason I say that it's displacement is because if Shively had been running at negative 8 meters per second, then that area would be a negative 40 meters. Okay? That's why we say that it's displacement. So, golden rule number, what are we up to, 7, roughly? Whatever. This is the last one. The area between a line on a velocity time graph is, wait for it, displacement. Okay? Doesn't matter the shape, doesn't have to be a rectangle, it could be a triangle, it could look like a squirrel. Doesn't make any difference. Okay? And again, for those of you that have done the calculus thing, if here's a velocity time graph, and you find the area underneath the curve, otherwise known as taking the, I'd call it integral, I think you guys call it like antiderivative or some weird voodoo thing. Okay? Basically, you're finding the area underneath here, which gives you the displacement. Now, that's only true on the velocity time graph. It doesn't work on anything else. Okay, good. Got it? Grant? Okay, so stop that for a second.
Does it just charge, or is it batteries, or what?
Are you so curious, Harry?
I'm just always interested.
He just wants to know, dude.
Dude,
What's
look.
wrong with it? What's wrong with
What if I'm-
expanding his knowledge
Yeah,
in
dude.
life?
Everything.
Maybe one day I'm.
You like the knowledge Nazi? No new knowledge for you today.
Got a knowledge Nazi.
recording.
Okay,
Yeah, I am.
so go ahead and start it up. Or is it
It's
all?
been
already
started
been
for about
going.
30 seconds.
Okay, so here's the deal. So the whole purpose of this lab is to kind of show us how this deal is going to work in terms of position time graphs and velocity time graphs. So what you're going to start with is this device. It's called a constant velocity device. Now, let's talk about what it is and what it isn't. So the whole purpose of this thing is oddly enough to move at a constant velocity, right? And because it's a constant velocity device as opposed to just like a toy, then the science supply companies can charge us a lot of money. Because if they just call it a toy, it would only be like $5. But since it's a constant velocity device, they charge like 25, even though it's the exact same thing. So here's what I don't want to see. There's a whole bunch of them back there. I don't want to see races. Okay. I don't want to see you tie a string between two of them and have like a truck pull. Okay. I don't want you to build a ramp and go, whoa, they'll climb up over it. Cool. Okay. I know it will. I don't want you to put 1.6 meters in between two of my tables and see if you can get it across the bridge. Okay.
I wasn't even gonna do that.
Now you gave us the
You
idea.
planted
This
the
is a
seed.
mistake.
Okay. This is an avoidance thing. Okay. And most importantly, I don't want you to like act like you were like in 5th grade playing with your Hot Wheels and going, boom, boom, boom. Okay. Not how you wind it up. Okay.
That's the beauty of maze.
As Honus
We
pointed
do
out, there are
that.
batteries. We don't need to store. Was that a plastic bottle that you just threw in my trash can?
No.
Really?
I thought that was recycled.
Cycle. Uh-huh. Nice recovery. It's your planet I'm trying to save, okay, for your kids and your grandkids. And what do? Throw it in the trash.
5% for the day, suffer.
Huh?
5% for the day, suffer.
Okay. Yeah, that's why I don't have any kids. Okay, so now what you need to make sure that happens, and this will play out large later on, you need to make sure that you know which direction it goes when you turn it on. Okay, that's going to be a key thing. You need to know which direction it's going to go. Now, here's what's another thing that's important. On this tape, there's like, it's metallic coating. So there's like a paper side and then the shiny metallic side. When you run it through the tape timer, which we'll get to in just a second, the metallic side has to be up. So hold off, and this is important. You need about yay much tape. Okay? It's a highly precise scientific endeavor. Yay much. Not yay and a skosh. Okay? Not a skosh less than yay. Yay much. If you're not sure if you're at a yay, ask me and I will tell you, do you have yay much tape? Okay? So you got yay much tape, tears easily, here you go. Now, so what's going to happen is that you're going to run it through the tape timer, okay? And it says spark timer because it makes little sparks. So there's two buttons to it, an on and off switch if you need help with that. There's other issues. There really are. It's like, seriously? Okay, now, but there is a button here that says 10 hertz and 60 hertz. What do you think the difference is? This isn't like the donuts, okay?
Interval.
Intervals. Hertz refers to like events per unit of time. So if you're at a 10 hertz, it's making 10 dots per unit of time. In this case, 10 hertz, 10 dots per second. If you're at 60 hertz, it's making 60 dots per second, which is really, really fast. So make sure that this thing is set on the 10 hertz side, not the 60. Make sure it's the 10 hertz. So what it's going to do is it's got these brass electrodes here. And what it's going to do is going to make those things vibrate back and forth. And when they do, it's going to create a spark, and you'll hear it. And that's the mark that's going to be left on this tape. So here's the sequence. There's a little arrow in the direction that you need to feed the tape through. Okay? A little arrow. Run it through in that direction. So you're going to run it through in that direction. Okay? Now, attach it to the machine and make sure that you know which direction the machine is going. Okay? Don't turn the machine on and then have it crawl back over the tape timer. That's not what we're about. Okay? You want it to make sure that it's going away from the tape timer. Now, also the sequence is important. Don't attach it to the machine first and then go, this is Burkamp, it won't fit. What am I supposed to do? Okay? I've had that happen. Not really, but it's a good story. So you're going to take that, right, feed that through, and should I hold this for stand? No, stand. Okay. So then you take a little piece of tape, taking advantage of some strong intermolecular forces, and you attach that. Now, this is important in terms of timing. So here's what you want to do. You want to turn the tape timer on first, then turn on the machine, because we want the machine to start from rest. Okay? So here's your sequence. Tape timer first, machine second. Make sure the machine's going away from the tape timer. Now, these are constant velocity devices. They are subject to gravitational fields. Make sure they don't fall off the table. Okay? We don't have the anti-gravity constant velocity devices, which would be really cool, but we can't afford those. Okay, so here's the sequence. I'm going to turn it on. Okay, cool. Then we turn on the machine, and we're off. Now, you obviously have longer tables, and you can pull the whole thing through before it falls off the abyss and starts to accelerate. So, what you will see is that, you can't see this from the back, but I'll draw it up on the board, is that you're going to see a series of little marks. You see? Okay? So there's going to be little black marks where that spark has been created. So this thing started from rest and then began to speed up. The tape timer is moving at a constant rate. So what do you think is happening to the distance between the marks? It's getting bigger. Why?
Speeding up.
Yeah, so more tape is being pulled through in each interval. Okay, so you just need one tape per group. Okay, that's all. Don't generate a tape for everybody. You're just going to generate one tape per group. Now, let's talk about what you're going to do with that information. So, on your data, on your lab, here's your data table, and this is, I think, displacement, and then, what's next, the total displacement, and then velocity.
Yes.
Okay, now I've already given you the units, centimeters per interval, centimeters. So, on your tape, here's what you're going to see. You're going to see a series of dots, and that's where you turn on the tape timer, but the machine hadn't started to move. Okay, so that's the first thing that you're going to notice. Then, after that, you're going to see a series of dots like this. So what you need is you need 12 intervals. So that's why I've got, if you look on your data table, there's 12 spaces. So just come in here and number them 1, 2, 3, 4, all the way up to 12. Okay, that's the first thing you're going to do. We're going to work in centimeters because these are going to be really small distances. So what you're going to do is you're going to measure the distance between where you started and that first interval. Okay, you're going to use metal rulers. They're pretty high precision. You know the tenths, and you're going to estimate the hundredths. Great?
Wait, what's the dots before the first?
This is where it was making the dots before I turned on the machine.
Oh, okay.
Okay? Make sense?
Yeah.
So you're going to measure this, and let's say that's 1.23 centimeters. Now, you don't have to write centimeters here, because I already told you what this column is going to be measured in centimeters. If you want to, that's fine, but you don't have to. So, your total displacement is going to be how far you have moved from the starting point at the end of each interval. So at the end of the first interval, how far had you moved? Yeah, don't make this difficult. Oh, I moved 1.23 centimeters. All right, that's simple. Now, your velocity. We're going to make an assumption that's going to make our velocity column simpler. Whatever this is, however far you travel in this interval, we're going to call that our velocity as well. Now, in reality, this is not true. It's not accurate. And here's the reason why. Because over this interval, you're actually speeding up. Okay, so you're actually going slower than this at the beginning and probably faster than this at the end. But without going through a whole bunch of math, this is just going to give us a nice idea of how fast we're going. Okay? So, 1.2, 1.2, or 1.23, 1.23, 1.23, whatever yours is, okay? Now, that's interval number 1. When you get to interval number 2, let's say that went up to exactly 2 centimeters, okay? So now, you're going to measure from interval 1 to interval 2. Don't go back and measure from the beginning. Now you're seeing how far it traveled in the second interval. This is a running total. So if I was at 1.23 and I traveled another 2 centimeters, how far have I gone?
3.23.
So this is going to be 3.23. Now, this velocity is going to be 2 centimeters per interval. Because we're saying this is how fast we're going. So your far left and your far right columns are going to be the same numbers. They're going to mean completely different things, but they're going to be the same numbers. Okay? So, you're going to do that for 12 intervals. What?
Why would the velocity be the same as the displacement?
Because this is how, what we're saying is that this is how far we're going per interval.
So, just want us to divide by 1 second.
No. Yeah, it's just whatever number this is you're just going to transpose it over here. There's nothing to divide. Yeah, but Hunter, you're right. Basically, we're saying this is how far we're going per interval.
Okay.
Yeah. So in that regard, yeah, you're dividing by 1 interval, technically. Okay? Got it. Now, you're going to draw 2 different graphs. You're going to draw a total displacement versus time graph and a velocity versus time graph. So your position time graph, when you get done, should look something like this. So this is going to be your position time. And then your velocity time graph. Is your velocity time graph going to start at 0, 0?
Yeah.
Why?
Because you can't have, at 0, seconds at zero velocity.
Yeah, I wasn't moving at the beginning. That's why you have to sequence that right so that the car starts at rest. So basically what's going to happen, in an ideal world, you're going to get something that looks like this. This is when the car is speeding up and your velocity is increasing, and then you kind of have a constant velocity. Now, here's the most important thing that you have to understand. Listen to me, listen to me, listen to me, listen to me. Both graphs have to show the same thing happening at the same time. So we said, if you go to a position time graph, what is indicated by an increasing slope on a position time graph? What's the velocity doing? It's increasing. And that's what's happening here on this velocity time graph. Now, a horizontal line on a velocity time graph indicates
Constant.
constant velocity, which is going to show up how on the position time graph? Not an increasing slope,
A straight slope.
a straight sloping line with a constant slope. Yeah, because what you said, it would continuously curve up like that. So, this is some of the questions that you have to answer, okay? Both graphs have to show the same thing at the same time. Now, realistically, this graph will probably have some dipsy-doos to it because it's not true constant velocity, and we have some pretty precise measurements. So this probably won't be an exact horizontal line, but it should be pretty close. Okay, now, one of the things that you want to do on number 5, it says, or number 4, you're going to calculate the average velocity for the 12 intervals. We talked about this yesterday. How do you calculate average velocity? And bar over it means average. What minus what divided by what? P minus P naught over time, right? Oh, come on. So, on this situation, what's my overall initial position?
0.
0, because this is where we started, right? Now, your final position is going to be the sum total of how far you went. Okay, that's your final position, because that's how far you went to the beginning. So this is going to be whatever point this is, minus 0. Now, we're going to look at this in intervals. So you need to divide by 12 intervals. So it's basically going to be the sum total minus 0 divided by 12. And then you're going to draw that on your graph. Pay attention to everything that I want on that graph. You have some questions to answer on the back. Due tomorrow. Go fly. Lab 3.